Oh yeah, so today we're gonna have the morning session will be delivered by Dr. Peter Spiritis, our guest lectures. He actually also gonna deliver another lecture tomorrow tomorrow afternoon. So I'm just gonna give a very brief introduction of Dr. Spiritis, who actually really needs no introductions. Dr. Spiritis is Mariana Brown Dietrich Professor and the head of Department of Philosophy at CMU. He's one of the pioneers who created the field of the causal discovery. He has a really interesting background. He earned his PhD in history and philosophy of science and a Master of Science in computer science from University of Pittsburgh. He conducts research at the intersection of philosophy, statistics, graph theory, and computer science. His work over the past several decades has focused on the Tetra project, a collaboration with several other faculty members in the Department of Philosophy. This project specifies and proves under what condition it is possible to reliably infer causal relationships from background knowledge and data not obtained under fully controlled conditions. Their approach to causal discovery constitute a breakthrough in fundamental methods in artificial intelligence. Tetra is perhaps one of the most well-known, most commonly used platform for causal discovery. It is free, open source, and supports modeling, model building and testing, full simulation, and implements dozens of causal discovery algorithms that can be executed on a laptop or on the Bridges Pittsburgh supercomputer. The software has been successfully applied to scientific problems, including economics, epidemiology, psychology, and education research. The Tetra team received an NIH Big Data to Knowledge Center grant to form the Center for Causal Discovery, which led to software improvements and a variety of new algorithms for special problems. In 2020, Dr. Spiritis and the Tetra team won the Super Artificial Intelligence Leader Award at the World Artificial Intelligence Conference in Shanghai. The award recognized fundamental advances in the basic theory, methods, models, and platform of artificial intelligence. So it is truly an honor to have Dr. Spiritis with us today through Zoom and deliver a lecture on history of modern causal inferences. Let's welcome our speaker.
Well, thank you for inviting me. What I'd like to do today is to consider sort of where things were in the late 1980s and early 1990s in terms of doing causal inference. Since that time, there's been an explosion of research in causal inference of various kinds, both in terms of making progress in making inferences from given causal models about what would happen if you intervened on the system, and in terms of inferring counterfactuals. And there's also been an enormous increase in research in finding algorithms which, given data, construct causal models. And I'd like to consider sort of what the situation was like when this sort of big bang of research started. So let me go back a little bit before the 1980s. Aristotle lived around 300 BC. The ancient Greeks at that time did not have a lot of what we would consider to be science, but Aristotle had a view of what science ought to be like, and it was largely focused on finding out what caused what. So he had a theory of causation. The word in ancient Greek is eikon. That doesn't exactly translate into English. It's usually translated as cause, but it could also be translated as explanation or make. And it was basically about answers to why questions. So Aristotle divided things into 4 kinds of causes, and several of these don't look like what we would call causes, but several of them do. So he had the idea of a material cause, and that was simply the material out of which a thing was made. So if you had a bowl, then its material cause was bronze or silver. He had a formal cause, which is difficult to explain, but the idea is that things have a pattern, and the pattern is what makes the thing what it is. So a house is a house because it's set up in a certain way, and it's got rooms and a roof and walls. And so that was sort of this pattern he also considered to be a cause. Then there get to be a couple which would sound like causes in the sense that we think of causes. The efficient cause is basically what we normally think of as causes. It's the source of the primary principle of change or stability. So the producer is a cause of the product. It's the initiator of the change. So that's fairly similar to most of what we think of as causes. And he also had the idea that there was a final cause, which was the function of something. So health is the cause of walking. So if you said, why is that person walking? It's to increase their health. If you wanted to ask, but it didn't just apply to things like people, which had beliefs and desires. It also applied to things which just seemed to naturally have purposes. So for instance, if you asked, why is the heart the way it is, you could say, well, because it's a pump. So I'm going to concentrate on the efficient cause. And as far as Aristotle was concerned, finding these causes was basically what science was about. This was going to be what scientists ought to do, and he had particular opinions about how you could use logic in order to discover causes. Of course, the ancient Greeks didn't have anything resembling statistics. They had the idea that some things occurred with probability rather than deterministically, but that was sort of the extent of what they had in terms of the idea about chance. So this was Aristotle's views about science and about what the point of science was. Reigned for several thousand years. As late as the 17th century, Aristotle was considered, the authority on what science ought to be like. And what science ought to be was to go out and discover causes of things. Now, in the 17th century, Aristotelian ideas got kind of a bad name. Because there were many Aristotelian scientists who seemed to be engaged in kind of a trivial activity. So if you asked why it is that a certain drug would put someone to sleep, they would say, well, the cause is that it has a dormitive power, which seemed pretty trivial, right? It just seemed like, well, you're just going to rename the effect and say that, I've explained it to you when all you've done is sort of to repeat that there's some cause in the drug without saying anything at all about what it's like. And Galileo in the 17th century sort of mocked Aristotelians for doing this kind of trivial discovery of causes. So in the 17th century, we get the scientific revolution, and there are advances in sort of all kinds of disciplines: chemistry, physics, celestial mechanics, optics, mathematics has this flowering, calculus for the first time. However, they still believed that the main purpose of science was to discover causes, but then they had particular ideas about what these causes were going to be like. They had to be mechanistic or atomistic explanations. So you would say, you would describe the mechanism by which things occurred. So it wouldn't be enough to say that the drug had some dormitive power. You were supposed to describe some kind of particles, I don't know, which would soothe the body and make it sleep. And but so there was the idea that these mechanisms, which were kind of hidden, right? It typically involved little small particles. But the idea was we could discover these by experimental manipulation, certainly, and we could also discover them, however, even without manipulations. And that's what happened with respect to celestial mechanics. The idea was that there was still going to be a method by which we could discover the hidden springs, which explained why it is that the planets were where they were, even without doing experiments. Because obviously there weren't any experiments that we could do on planets and stars. So this suggested that there should be a search for a method of search, a method of scientific discovery. So, so a lot of sort of what, in terms of modern view of science, comes out of this scientific revolution. First of all, there's going to be equations which relate various quantities to each other, and these will be causal equations. We will explain things by telling which forces were exerted on which bodies according to which laws. The idea that we should relate manipulation to causation also plays an important role now, because people believe that they have an experimental method, and that the experimental method is explaining things and helping to discover causal relations. So we have the connection between the idea of manipulation and causation, and we also have the idea that we can search for a method even if we can't do the causes. So the grand flowering of all of this is ultimately in Newton's Principia, which is sort of the most influential textbook since Euclid's geometry, and Newton comes up not only with celestial mechanics and the rules, Newton's 3 laws, and the force of gravity. He also comes up with an explanation of how it is you're supposed to discover things, even if you can't do experiments. So he says, no more causes of natural things should be admitted than are both true and sufficient to explain their phenomena. So in Latin, that's the true causes are the vera causa. So again, the point of science is to discover the true causes. The rest of these are basically the rules by which he attempts to justify his universal theory of gravitation. So he wants to say the causes assigned to natural effects of the same kind must be, so far as possible, the same. So if I know that there's this cause of gravitation, and I can explain things with gravitation, then I should use gravitation as, I should infer that gravitation is the cause. The third one is less important for us, the qualities of bodies that cannot be intended and remitted. So qualities that cannot be increased and diminished, and that belong to all bodies on which experiments can be made, should be taken as qualities of all bodies universally. So here, again, he's trying to say, okay, we can do experiments over here, and that tells us something about bodies. And even if I can't do the experiments, there are situations under which I can extend what I learned via experiments to everything else. And the fourth one is kind of a dig at Descartes. He's saying that propositions gathered from phenomena by induction should be considered either exactly or very nearly true, notwithstanding any contrary hypotheses until other phenomena make such propositions either more exact or liable to exceptions. So Descartes had lots of theories about how particles were bouncing off each other and what the laws were, without sort of any evidence of what these things existed or how they were acting. And Newton was saying you can ignore all of that stuff and just consider the fact that I've got the universal law of gravitation. It explains all of this stuff. Bodies have masses. I get to apply it everywhere. And the fact that you can dream up some story about how things are acting, that's not anything you should do until my theory, which explains all this stuff, has shown some kind of problems. So that's sort of the long-term background. But I did want to give you that theme because that theme about what role causation plays in science is something that's going to come up repeatedly. And much more recently than ancient Greece or the Middle Ages. In particular, the question of, is science about discovering causal relations, or should we kind of ignore the causality part? Part of what people were disturbed about with the Aristotelians in the Middle Ages was they thought that causality was kind of a very mysterious idea. We didn't really understand what causality was. What does it mean to say that A causes B? And while it played a very central role in Aristotelian philosophy, and hence the view of what science could be, around the time of the scientific revolution, there began to be doubts about whether, whether it was being used in kind of this trivial fashion. Did we really understand what causation was? And ultimately, after the scientific revolution, philosophers began to question whether there really was any such thing as causality. So Hume basically said, look, we never observe an event A causing an event B. We don't ever see that. We see the event A and then we see the event B. And really all that we have with causation is that we saw A happen a bunch of times, and then afterwards we saw B happen a bunch of times. And so there was this kind of constant conjunction between A's and B's. And so naturally we thought, well, when I see A, I'm going to see B. But there really wasn't anything more to causality than this kind of constant conjunction. So on the one hand, there were a lot of people who took causation to be a kind of the central point of science, and there started to be people who considered causation to be, well, maybe there's not really anything there at all, and that we need to do science without causality. So that theme will come up again in the 80s and 90s. And what I'm going to do in this talk is sort of go over what the state of beliefs about causality was in the 1980s and 90s, what kinds of causal models existed, how people represented the idea of doing a manipulation in those causal models, what assumptions were being made, what inferences of effects were made at that time, and sort of the beginning of modern ideas of a search for causal models. So let me start with causality. And as I mentioned, there sort of grew up to be two camps, and one camp really questioned whether causes existed. So Bertrand Russell, who was one of the great philosophers, but also one of the great mathematicians of the 20th century, said the reason why physics has ceased to look for causes is that, in fact, there are no such things. So he thought it was this mysterious relationship between events that nobody really understood, and people were just fooling themselves into thinking that this was sort of, you had some kind of understanding when you said that one event caused another event, and that there was no satisfactory definition of cause. So he said it was so inextricably bound up with misleading notions as to make its complete extrusion from the philosophical vocabulary desirable. So he wanted to get rid of it in philosophy, and he also thought that it was playing less and less of a role as science developed. This actually intruded upon kind of modern views of science as well. So if you look in particular at econometricians, there's the view that many econometricians are apt to be uncomfortable when thinking about the concept of causality. And on the one hand, it seems like a primitive notion which is indispensable. And on the other hand, it's notoriously difficult to formalize, as casual reading in the philosophy of science will attest. So there have been sort of multiple attempts in philosophy to define causality in terms of something else that we understand better. So Hume tried to define it in terms of this idea of temporal order and constant conjunction, that A caused B when A was before B, and whenever I saw an A, I later saw a B. People have tried to define it in terms of probability. People have tried to define it in terms of counterfactuals, although the idea of a counterfactual is itself somewhat difficult and mysterious to understand. None of those definitions proved very satisfactory in terms of how we actually attribute causation to things. But what we'll see in econometrics and in lots of other disciplines is that there was a tension between the idea that on the one hand, we really needed to understand causation, and on the other hand, we didn't really have any good ways of discovering causation if we couldn't do experiments. And so there was the view that, well, we couldn't be making causal claims in science, at least, if we can't do the experiments. So what we ought to do is to say, well, science is about the stuff we can do, and none of that stuff is causal. So I can write down equations in econometrics, but I shouldn't interpret those equations as being causal or being about what would happen if I were to intervene on the system. They're just equations that describe the state of the system. So if we go back and think about earlier examples, when Newton came along, people were pretty good at predicting the positions of the planets, and they used Ptolemaic astronomy. Ptolemaic astronomy had this picture that the Earth was in the center of the universe, and there were spheres around the Earth, and that each planet rotated on a sphere, but each sphere had little circles or epicycles, which as the big sphere rotated, the little sphere also rotated, which created this kind of non-uniform motion. And by putting in enough epicycles and various other kinds of tricks, you could predict the positions of planets pretty well. There certainly wasn't any better way to predict the positions of planets until Newton came along. Now, Newton's explanation does seem to be causal because there aren't these sort of imaginary crystalline spheres and things, little epicycles on top of cycles and epicycles on top of epicycles. It was instead a system of equations whereby it would tell you if you could put a mass in this position, this is what would happen to the system. And the masses really existed. And if you could just do the experiment, you would see what the results were. Whereas, if you wanted to know what would happen under Ptolemaic astronomy, it just wasn't at all clear that it gave you any kind of answer. It was all about simply saying where the planets would be in the future, not what would happen if you could intervene on them. So this tension certainly occurs not just in sort of ancient physics, but also in things like modern econometrics, where there's a disagreement about, should I be interpreting these equations causally, or should I just say they're equations which tell me, which allow me to predict the future, but not what would happen if I intervened on the system. So what kinds of causal models? So there were causal models, nevertheless, in the 1980s and 90s, despite some doubts about whether or not we should be interpreting things causally. And I'll briefly describe what those were. So there were structural equation models, there were graphical causal models, there was the potential outcome framework, there was Granger causality, and there were some regression models. So let me just say a little bit about the history of those and how people used those and interpreted those. So around the turn of the 20th century, Sewell Wright came up with the idea of a structural equation model. And this diagram here is generally taken to be the first structural equation model. It's about guinea pigs, and it's about the relationship between the parents' guinea pigs and the child guinea pigs. So you'll note that he's got arrows in the diagram, and those arrows are to be interpreted causally. So we have the sire and the dam. We have observed features of the child. You'll see that we have the D's and the E's outside of that are exogenous variables. So those are kinds of noise terms. They're exogenous variables. You can see that there are coefficients next to each edge, and those coefficients are basically taken to be linear coefficients in a model. So G is taken to be B times H plus C times C. So I'm talking about this G here is B times, H double prime plus C times C. You'll also see that there's a double-headed arrow, which represents a kind of correlated error. And this was, so what he wanted to do was to use these causal diagrams, associate the causal diagrams with the corresponding linear equations, and interpret the linear equations as being about causation, right? So you weren't simply saying that if you told me here are the genetics of the sire and the dam, this is my prediction about the characteristics of the child. It's that if you were to manipulate the genetics of the sire and the dam, you would get changes in the distribution of properties in the child. So, and this gets back to this theme about, how are we supposed to interpret these equations and what do we make of them? So to quote Shipley here, there was a phenomenalist school of Pearson, and they didn't like the idea that Sewell Wright's notion that you could even distinguish causes from correlations, that there was going to be any difference between telling me the causes and just telling me what the correlations were. Now Fisher, who was maybe the greatest statistician of the 20th century and deeply involved in the idea of a randomized clinical trial, did believe that there was a distinction between causation and correlation, but he believed that the only way you could study causes was by doing the experiments, right? If you didn't do the experiments, then you couldn't reliably draw any kind of conclusions about what the causes were. So that meant that, as far as he was concerned, that that science had to be about doing experiments, and anything else wasn't really science. Now, around the same time, Caverian Speed and then Pearl came up with this idea of using directed acyclic graphs to represent probability distributions. And the idea is that a DAG represents a distribution when each variable is independent of its non-descendants, conditional on its parents in the DAG. So in other words, this graph represented a set of probability distributions, all of which shared the same conditional independence constraints. So, for instance, we could say that college plan CP is independent of sex, conditional on parental encouragement, socioeconomic status, and IQ, that sex is independent of socioeconomic status, and that sex is independent of IQ. So there's a graph, there's a set of probability distributions associated with the graph, and the idea here is that we're representing that set of probability distributions with the graph. And if we do that, that allows us to actually to find out, or rather to calculate conditional probabilities quite easily. So particularly with respect to discrete distributions, if I had a lot of variables and you gave me the joint distribution, it was computationally quite difficult to calculate an arbitrary conditional probability. But these graphs, using these conditional independencies, were able to speed that process up enormously. And originally, that was kind of the main point of having a Bayesian network, to be able to calculate a conditional probability quite quickly. Now, you can give a causal interpretation to the DAG as well. You could say that it represents a causal structure, so that if I draw the DAG illustrated here, that the edge from drinking to smoking means that drinking is a cause of smoking. And that smoking is a cause of cancer. So later on, we'll talk about how you would link up these two different interpretations. But adding this causal interpretation on top of the probabilistic interpretation was something that took a little bit of time for that to happen. So when Pearl originally introduced Bayesian networks and the probabilistic idea of a graph, he did say that you could interpret the edges causally, but what he meant by that is simply that that's the way people conceive of the world. He thought that people thought about the world causally, and there was no indication that you could use the causal graph as a tool for predicting what happened when you made interventions on the world. It was simply a convenient way for people to think about the world. Here, so in our work, and I think also to some extent in Convery and Speed, who were earlier than Pearl, I think they thought of that as causal as well, although they weren't explicit about how you would relate it to manipulations. There's also another school of thought, which is the potential outcome school of thought. And this is based on the Neyman-Rubin model. And the idea here is, and this is kind of a key advance, is that they have a notation for interventions versus conditioning. So Neyman around the turn of the 20th century, and then later Rubin in the 70s and 80s extended this idea away from just doing experiments, but to other, more generally, that I could introduce y sub t of u, and interpret that as the value that unit u, that's an individual in the population, would have if u had been assigned treatment. And y sub cu is the value that unit u would have if u had been assigned control. So there we have sort of now, this is clearly a causal model. It introduces the idea of interventions, and it's got a way for distinguishing between the idea of conditioning versus the idea of intervening. And Rubin extended this idea that we could expand this from experimental context to general contexts. Now, another sense of causality that was around at the time was Granger causality. And Granger causality basically had the idea that we would say that if I had two time series, then I would say that time series X was a Granger cause of time series Y if including the information about X gave me a different probability than leaving that information about X out. So that's the difference between I of t and I minus X of t. And here we say, here we have, here I'm leaving X out. That's giving me different probabilities than leaving X in. And in that case, we say that X is a Granger cause of Y. So I of t and I minus X of t, that's supposed to be all the information in the entire universe. And I minus X is the modified universe is in which X is excluded. So this is basically a kind of conditional independence test for whether X causes Y. Under very strong assumptions, in particular, that you can use, that you have at your disposal all of the information in the universe. Now, in practice, of course, you don't have all the information in the universe, and instead of using general ideas about probability, typically what people did was to assume linearity. So I wouldn't take this as a kind of definition of causation, although it was sometimes treated that way. It's more of a test for causality under a very strong set of assumptions. But it was widely used in certainly in econometrics. Now, there are relationships between these different kinds of causal models. Basically, a structural equation model whose functions are represented by a DAG. So you take the DAG, the edge to exist between X and Y, when Y is a function of X, and that there are error terms that are independent. and that's a special case of a DAG graphical model. However, structural equation models, as Wright conceived of them, also allowed for correlated errors, which were those double-headed arrows, and cycles, which were to represent feedback. So you could take a DAG to be kind of a special case of a structural equation model. The potential outcome models, are they fundamentally different than the DAG models or the structural equation models? So there's been a lot of argumentation about whether these two things are fundamentally different. However, I think there's an article by Robbins and Richardson, I don't know why I have question marks there, that's in the bibliography, which sort of gives a translation back and forth between potential outcome models and graphical models. So at least from the people who do structural equation models and graphical models, potential outcome models are a different way of talking about much the same thing, although there are a lot of potential outcome people who think that the structural equation model people are talking about something fundamentally different. So from my point of view, they're basically different ways of talking about the same thing. So we had basically the right kinds of causal models existing. We had the kinds of causal models that we're using today existed in the 1980s and 1990s, and they had existed for quite some time. The structural equation models that Wright came up with were at the beginning of the 20th century. Neyman had been writing early in the 20th century. The idea of the graphical models representing a set of conditional independence relations was actually, that one was more recent, but certainly by the late 1980s that had been established. So, okay, we have these kind of causal models. We have the idea has been introduced that we can use them to predict the effects of manipulations or interventions. I'm going to use those terms interchangeably. How are they represented within these different models? Well, within the causal DAG view, where each edge represents a causal relationship, you can take what's called a hard manipulation of a causal DAG, which just breaks all the edges into the variable being manipulated. So you can, in the case of this causal graph, if I manipulate smoking, then I just break the edge between drinking and smoking. And that's now the manipulated graph. That's a representation of the new system where I've prevented drinking from having any effect on smoking. I could do that, of course, by doing a randomized experiment and simply assigning you to smoke or not smoke. Or I could do that in a variety of different ways. When I do that, I've now introduced a new independence relation. Smoking is now independent of drinking, where this symbol represents, turnstile symbol represents independence. So, so as far as the graphical models are concerned, you introduce manipulation by breaking edges, and then that introduces new independence relations. In terms of structural equation models, what is an intervention? Well, that is all I have to do is take my original set of equations, and if I'm say manipulating G triple prime, which is down here, I can do it simply by crossing out the original equation, which relates G triple prime to its causes, and replacing it with a new equation which just sets G triple prime to some constant. This was not something that Wright introduced when he introduced structural equation models. But that was explicitly introduced by Strauss and Wald, who were two econometricians in 1960. So they were perfectly explicit about this is the way, there's a distinction between interventions and conditioning, and this is the way that you represent interventions in structural equation models. So in that sense, from 1960 on, you had a way of saying, this is what we mean when we say we're interpreting these equations to be structural equations. We mean that when there's a method of representation of interventions which consists of crossing out the original equations and replacing them with new equations. And the idea here is, of course, that these equations are representing sort of individual little mechanisms relating pieces, one quantity like G triple prime to other quantities like H triple prime and to C. And if I give you all of the pieces, then that together determines how the whole system interacts. So a lot of people who were sort of in econometrics and ultimately in other social sciences were perfectly clear about how interventions entered into the system and what made the equation structural. However, there were also a lot of people who called them structural equations. If you had asked them what makes them structural, really wouldn't have a very good answer. So it was interesting that the answer was there and that it had been understood by a lot of people, but it kind of got lost for a while. And people were somewhat confused by why these equations were supposed to be structural equations. Now, in potential outcomes, of course, the terminology is, the representation of manipulations is built into the terminology. Y sub TU, it's the value that you would have if you had been assigned treatment. So the idea here is that if I have this kind of ideal intervention, YT sub U, YT of U is the value that you would have under intervention, which is to be distinguished from the conditional probability, which would be simply Y conditional on something, using the bar to represent conditioning. So, so we had the causal models. We had at that time an understanding, certainly by the late 1980s and early 1990s, what the distinction between manipulation and conditioning was. And now let me say something about search. There was, as I've mentioned earlier, a lot of question about the extent to which it is possible to make reliable causal conclusions when you don't have experimental data. And that is going to play, those doubts about whether it's even possible are going to play an important role in understanding why it is that there were a lot of controversies about search algorithms and the extent to which the whole enterprise of trying to use non-experimental data to reliably draw causal conclusions even makes sense to begin with. So I'll return to that in a few minutes. And let me just say that the reason I wanted to mention that is that there were ultimately some assumptions that were going to have to be made in order to relate causality to probability, which is what is going to, and those assumptions are going to play a key role in making these algorithms reliable. So let me just start by defining causal sufficiency. So a set of variables is causally sufficient if every cause of two variables in the set is also in the set. So in this particular case, if I give you parental encouragement, socioeconomic status, IQ, and college plans, that's causally sufficient. But if I gave you just IQ, college plans, and socioeconomic status, that is not causally sufficient because I would be leaving out the let's see, what am I leaving out? There's a cause of two variables in the set. IQ. Yes, IQ and college plans have a common cause, socioeconomic. Oh no, that is in the set. Let's see. Oh no, I don't remember which common cause am I leaving out. IQ. Well, I'm sorry, I don't recall. If I just gave you parental encouragement and college plans, that would not be causally sufficient because I would have left out socioeconomic status, which is a common cause of parental encouragement and college plans. So what are the assumptions that relate these causal models that are made about these causal models? And of course, there's three different kinds of causal models I'm talking about. So the assumptions are stated somewhat differently, but there's actually a fair number of them that they have in common. So in terms of structural equation models, we're saying that each structural equation represents a manipulable mechanism. So that is that I have each potential outcome is well defined. So that if I tell you what the manipulation is, there's a well-defined outcome. In the case of structural equation model, in the case of DAG models, it's usually assumed that the causal structure is represented by a directed acyclic graph, which can, in some cases, for instance, leave out feedback mechanisms. It's typically assumed that each unit in the population affects only itself. That is, my properties affect my properties, but they don't affect your properties. So if I'm a unit in the population, then my smoking affects my lung cancer, but my smoking doesn't affect your lung cancer. Of course, that can be false, but that's a special case that is usually not included in the assumptions that are made. There's a causal Markov assumption, which says that if a set of variables is causally sufficient, each variable is independent of its non-effects, conditional on its immediate causes. And finally, there's usually some kind of simplicity assumption. So in the case of structural equation models, we have the causal Markov assumption, which says each variable is independent of its non-descendants, conditional on its parents in the causal DAG. And then we have a faithfulness assumption. That's a kind of simplicity assumption, which says that all observed conditional independencies are entailed by the Markov condition in the causal graph. So one of those, the causal Markov condition, allows me to go from graph to independencies, and the causal faithfulness condition allows me to go from independencies to graphs. Okay, so let me postpone this until later. Now, there's often a whole slew of unmentioned assumptions that you don't have too many variables, that your sample size is big enough, that you don't have, that the units that you have selected were done on a random basis, that you don't have measurement error or missing data or multiple data sets from different contexts, or nonlinearity or non-stationarity, or mixtures of distributions or mixtures of structures or non-causal relationships. There's many different assumptions being made. And one of the things that we're going to see is that these all served as reasons for people to doubt that there could be kind of non-experimental discovery of causal relationships that was reliable. So we're going to see later how we're going to start off by making a few strong assumptions, but gradually reduce the strength of the assumptions that we're making. So another thing that happened in the late 1980s and early 1990s is that there were some important advances in inferences of effects from causal models. So Jamie Robbins showed how you could make inference of effects in partially confounded sequential experiments. So if you did a series of experiments, but there was some confounding that existed, you were still able to infer the effects even though you hadn't measured all of the relevant variables. And then in 1993, we found rules that were basically equivalent to the do calculus that had possible latents. And in 1995, Pearl came up with the do calculus applied recursively, so it greatly extended the set of conclusions that you could draw. So I'm going to put those aside for the moment and consider really what's the main topic here, which is the topic of search. So I guess this is an hour into it. Maybe we could take the break at this point and return at in 15 minutes.
Yeah, sure. Sounds good. So we're going to have a break now, and we're going to be back at 10:45.
Okay. Yeah, so let me start, let me just say something about the history of search. So I'm going to talk about two kinds of search. One is causal structure learning, and the other is causal representation learning. And I'll describe the differences in a minute. So we're going to assume that, that we have as inputs some data which is either observational or experimental or some combination of those. We have some optional domain knowledge such as temporal order, known causes, known non-causes. We've got some assumptions like causal Markov assumption, a simplicity assumption, possibly assumptions about selection bias or latent variables, etc. And what we want to output is either a causal graph, a set of causal graphs, a probability distribution over causal graphs, one of those kinds of things, something that gives us some information about what the true causal relationships are. For causal structure learning, we want to predict the effects of intervention among the variables that have been measured. And for causal representation learning, we want to find causal relationships between variables that have not been directly measured. So for example, if I'm interested in relationships between various personality traits, one thing that I might do is to give people questionnaires about their personalities. Excuse me one second. About their personalities, and use those to make inferences about the personality features themselves. So I don't directly know how to measure your level of conservatism, but I might measure that by asking you a series of questions. But what I'm really interested in is not the answers to the questions, but how conservatism relates to authoritarianism or something like that. So let me start with causal structure learning and talk about this particular case, because it's one that sort of played an important role into what we were thinking early on. So this is the alarm network. And it is a representation of the causal relationship between a bunch of alarms in an intensive care unit. Now the graph, the causal relationships came from a domain expert who knew how these alarms and quantities were related to each other. The data was not real data. It was simulated data from this causal structure. It has 37 variables, which have between 2 and 4 values, and it has 46 edges. Now, by today's standards, that's not a very big graph. But one of the things that happened in the 1980s and 1990s, which led to sort of an explosion of interest in automated search, was precisely that the size and numbers of data sets were growing exponentially. So this was discrete data that had been simulated. And if you look at the sort of standard textbook at the time for the analysis of discrete data in graphical models, well, they weren't using directed graphs, they were using undirected graphs. But they were, the examples are typically 4 variables, 5 variables, 6 variables. And so 37 variables would have been a really big graph for that time. Of course, today, you know, we could have, if we do fMRI data, it might be hundreds of thousands of voxels. If we look at genes, it could be, you know, 30,000 genes. If we look at SNPs, it could be 1 million SNPs. If we look at climate data, you know, it could be in the millions. So these are sort of tiny graphs, but by the standards of the time, they were quite large. And so this, just the sheer number of variables here would have presented difficulties for doing analysis. And that's partially for the following reasons. Suppose we had a large sample that was 10,000. So that would have been a big sample at the time. The size of the state space is the number of different possible combinations of values for those 37 variables is on the order of 10 to the 16th. Now, what that means is that if you sort of consider a giant hypercube with 10 to the 16th cells and 10,000 sample points, that means most of the cells, that is, any particular combination of values that the 37 variables could take on, are empty. So it's just this vast empty space with a few points distributed, clustered in a few cells. Furthermore, the number of DAG models that you could create out of 37 variables is on the order of 10 to the 237th. So it wasn't as if it was clearly going to be the case that you couldn't look at all of those models, no matter how fast your computers got. And remember, they were enormously slower than they are now. You couldn't possibly look at those, no matter how fast your computer was. So you needed to be able to draw reliable conclusions without looking at most of the models. So just these problems, the size of the state space, the number of different DAG models, and the fact that there's a kind of non-identifiability. That is, there are multiple DAGs that represent the same set of distributions. So without further assumptions, there isn't going to be any way at all that I could use a particular distribution to draw a correct conclusion about what the right DAG was. Because there would be these alternative DAGs which could have produced exactly the same data with the same probability. So we took those to be sort of, let's take those to be the major problems that we're going to deal with. And forget all the other stuff, right? There's all the stuff about what if I had latent variables, what if I had selection bias, what if I had measurement error. So all of the real data problems, let's put those aside and just think about those three and how hard they are for drawing causal conclusions. Now at the time, people weren't doing any kind of automated searches, and they often weren't doing formal statistical tests of the models that they hypothesized. They were tended to use background knowledge, and then they would look at something like the strength of association, how specific the association was. That is, did you have, were you able to predict specifically what had happened? They had temporal information, they had plausibility, so they had a lot of heuristic features that they were looking at. But there was not any kind of formal search that was being done, and there was not any kind of statistical test which gave you exact results. And this was in contrast to the way, for instance, estimation was done. When people did estimation, they would state exactly what the assumptions were. We have a linear Gaussian model, and then they would be able to say, give an algorithm which took that the data in, and then they would say, here's a proof of the properties of my estimator. So it might be pointwise consistency or uniform consistency. But with respect to the causal part, there wasn't anything that looked like that, right? There wasn't anything around where people could say, well, here's my algorithm, here are the assumptions that I made, here's a proof that the algorithm will give the correct results under the assumptions that I have made. We had instead this kind of much more heuristic kind of reasoning that was done. So what did people do? Well, you could use factor analysis, but and factor analysis, what could you prove about factor analysis? Well, there were actually two different interpretations of factor analysis. One interpretation was a non-causal one. It was just a compact representation of the distribution. And certainly you could prove things about factor analysis under that interpretation. But under the causal interpretation, there weren't any proofs under which it would give you the correct answer. And it made extremely strong and usually implausible assumptions, such as no causal relationships among the measured variables. And there was a kind of underdetermination. Rotations would mean that causal relations, you could always rotate the relationships among the latent variables, and you'd get different answers out. People, of course, you could do regression, and people did lots of regressions. And people did have algorithms for doing regressions. You could do step forward regression, step backwards regression, forward backward regression, all subsets regression. But there really wasn't any proof about any kind of causal interpretation of what the regression coefficients were. You could prove things, again, about sort of interpreted non-causally. The regression coefficient gives you a kind of relationship between the variables, but it's not necessarily a causal relationship. If you regress on the correct variables, then you can interpret the regression coefficient causally. But if you just do an arbitrary regression, the number that comes out is not a causal relationship between the variables. So if x caused y, of course I could regress y on x and get a regression coefficient, but I could also regress x on y and get a regression coefficient, and clearly that was not a causal one because it was backwards. So in practice, the advice was to regress on as many variables prior to the regressor as possible. This did not take into account the problem of unmeasured confounders. And it turns out, for example, that if you regress on too many variables, you can make estimates of structural coefficients worse when there are latent confounders. So in this kind of case where L1 and L2 are latent confounders, and X and Y and Z are measured variables, if I regress Z on X, then the regression coefficient will be 0, and it will equal the structural coefficient. But if I regress Z on X and Y, then the regression coefficient won't be 0, and my regression coefficient will not be equal to the structural coefficient. So there was, again, sort of no proof that under what conditions regression would give you the right answer. And there wasn't a reasonable kind of search which said, we will search for the right set of variables to regress on. There were a variety of heuristic searches that people used. There was a structural equation modeling package named Lizrel, which had something called modification indices. And the idea was that if you could start, you would make up a model, and then you would try and fix it by doing a search around this original model. This did not work well in practice, and the further the original model was from the truth, the worse it performed. We had Granger causality, of course, as a test for causation. But again, in practice, it assumed linearity. It also assumed there were no latent confounders, and it also assumed there was no instantaneous causation. So again, it was not a reliable method in most instances for being able to find causal relationships. So as I had mentioned, there was a lot of belief that, as a matter of fact, automated search was simply impossible. So part of the reason was that doubts about causation itself. So as Shipley mentioned, we had these causal models, say structural equation models, that came out of Wright's work. And as he noted, the Pearson school didn't think that you could distinguish causes from correlations at all, that it didn't make any sense to make that distinction. Fisher believed, he was a realist, he believed in causation, but he didn't think you could study it by looking at correlations. You had to do experiments. So there was this general belief that certainly if you didn't have experiments, you couldn't possibly draw reliable causal conclusions, and hence that the whole idea was kind of a red herring. So in particular, Fisher was extremely influential in this view. He believed in causes, unlike some of the statisticians. He just didn't think you could find them without doing experiments. He being the sort of discoverer of the analysis using randomized causal experiments. No experiment, no probability distribution, no causal inference. And in particular, he worried about unmeasured confounders. So towards the end of his life, Fisher became somewhat obsessed with proving that smoking doesn't cause lung cancer. So this was in the 50s, and this was before the government or epidemiologists had announced that smoking was a cause of lung cancer. People had long suspected that it had caused lung cancer, and there was an extremely strong correlation, or I should say, the increased probability of lung cancer given smoking was enormous. But of course, generally speaking, we couldn't do experiments whereby we forced a bunch of people to smoke and forced other people not to smoke and then waited 30 years to see what happened. So there was a lot of statistical evidence that people had gathered, and they had measured everything they could think of, and they had conducted, they had looked at conditional probabilities of all kinds that they could think of. And no matter what they conditioned on, they saw that, as a matter of fact, it was still the case that the probability of lung cancer given smoking was much higher than the probability of lung cancer given not smoking, no matter what else you could think of conditioning on. So Fisher had an explanation for this. He thought there was this, what happened was you developed lung cancer early. That early lung cancer manifested itself as a kind of lung irritation, and the lung irritation caused you to smoke. And at the same time, then the early lung cancer developed into the full-blown lung cancer. So because we weren't capable of measuring the early lung cancer, we couldn't condition on it. And because we couldn't condition on it, we always found that there was this higher probability of lung cancer given smoking than lung cancer given non-smoking, no matter what we conditioned on. Well, you can see from the picture why Fisher might have wanted to believe that smoking didn't cause lung cancer. But it was actually quite, this was, the data was still being gathered and the analysis was still being done. And there were lots of advertisements which did indeed advertise, that if you had the right kind of smoking, it would be less irritating, and people put menthol into cigarettes to kind of soothe your throat. So this was not an unreasonable view at the time, necessarily, but Fisher took that as a kind of argument against the idea that this idea that no matter how many things I had measured, it was always possible that there was a kind of unmeasured confounder, which was creating this correlation and conditional correlation between variables, meant that I couldn't ever do an analysis of the data which was reliable unless I was able to do the experiment. If I'd done the experiment on say early lung cancer, then I'm sorry, if I had done the experiment on early lung cancer, then I would be able to determine whether the early lung cancer caused smoking. But if I couldn't do that experiment, then for whatever reason, I just wouldn't be able to determine whether smoking caused lung cancer or whether there was some kind of common cause with an unmeasured confounder. Again, you saw somewhat of the same thing in econometrics, which I had mentioned earlier. So econometricians had come up with vector autoregression models, which for our purposes are just a kind of time series structural equation models. And some of them, and structural equation models, had been adopted early by econometricians starting in the 30s. And they would write out long series of equations and say, this is what causes what. And they would use that to make policy recommendations because they knew how to figure out what these equations said about what would happen if I were to intervene on the system. Now, the reply to that, against that, came from a lot of econometricians that said, well, you just made up a whole bunch of equations. And they actually did have a lot of variables, unlike most of the other social sciences. And they said, well, you couldn't possibly know whether these are the correct equations. You're just making it up. And you call it background knowledge, but you don't actually know whether any of this stuff is true. So that's not really doing science. So we shouldn't interpret them that way. We should just say, these are equations which, if we adopt these equations, then they allow us to calculate correlation matrices, and we can see whether those correlation matrices are approximately correct on real data, and that's what the science is. And so we should just forget all the causation stuff. And then the structural VAR people would say, yes, it's true, you have algorithmic methods and you can prove things about what those algorithms do, but you're not answering the questions that we want answered. People want to know whether or not, what we should do in terms of policy. And if I don't give these causal interpretations, then you're not doing science either. Right? So the structural people are saying you're not doing science because you're not answering the questions about causation. And the non-structural people are saying you're not doing science because your methods don't have any kind of guarantee of reliability. Now, another kind of argument against automated search that was raised was we don't have any automated searches that work, which in terms of getting causal relationships out was correct, but it wasn't an argument that there aren't any that could work. It was just an argument that they didn't have any that did work. So if we look in sort of 19 articles in regression textbooks in 1978 and 1988, we see that, well, people say, sure, I can see these correlations or dependencies between variables, but they may be due to lots of different things. So this is the correlation is not causation idea, right? It could be that X caused Y, it could be that Y caused X, and I don't know which direction is correct unless I have some background knowledge. It may be that X causes Y and Y causes X. So this could either be a case of feedback or of mixing different structures together. Maybe in some people X causes Y, and in other people Y causes X. It could be there's some third variable that causes both, and I haven't measured that, so I would have unmeasured confounding. It could be that the sample is not representative. Well, that's just a sampling problem, so usually we can deal with that in terms of saying how probable it is that I would get a sample that looks like that. So that's not one we're going to worry about. And they also, there was the question of whether X and Y formed a time series, and so I had non-IID sample. So people brought up these kinds of arguments against automated search, which is part of the list that I had given you earlier, that all of these things were things that we would have to worry about, and so that, we don't have any searches which are able to distinguish these different senses, and so that's and so none of this is reliable, and it was just then pessimism about whether it could be reliable. You know, people recognized they said correlation is not causation. It was quite common to make that claim. That's a kind of worst case argument. So if I have two variables and all I have is a correlation, and say it's a Gaussian distribution, then it's true. I can't determine whether X causes Y or Y causes X, or something causes both. It doesn't say that the worst case is every case. And so from our point of view, these arguments were sort of very much overly pessimistic in the sense that they took what we didn't know how to do currently as indications that we would never know how to do that. And again, you don't have to just use associations. There's more information in probability distributions than just associations. So if you look in 1980, there were sort of prominent people arguing against the idea that automated search was possible. So Terry Speed, who was one of the founders of graphical models, visited CMU. When he didn't publish this, but when he spoke to us, it was sort of like, yes, there may be better search methods than regression, but all of these search methods are dangerous in the sense that people will misuse them and not recognize the assumptions that are being made by better search methods. So it would be dangerous to put these tools out there and have people misuse them. And to a certain extent, it's true. People will misuse whatever is put out there, but that didn't seem like the best argument was to not find better search algorithms. Rubin was also sort of the main proponent of potential outcomes, basically thought that search was impossible. You don't even know what the right variables are. Remember that the variables that he's interested in are sort of the variables that have the interventions as subscripts. So he didn't even think that we didn't even know what the right variables were unless you already knew a lot about what the causal relations were. And Pearl, in the early versions of Bayesian networks, also was pessimistic about causal search. He thought that similar to what Fisher thought, no matter how many things you've measured, there could be unrecorded, unknown causes. So we really can't use these to estimate causal relations. And of course, as I mentioned earlier, there's sort of a whole slew of problems that you would have to worry about. Now, this was not, this list here of from Andrew Gelman wasn't around in 1990, but he sort of made up a list of when should we trust the output of a search procedure. This is something he made up rather recently, but I thought it was interesting because if we went back and looked at 1990 and asked ourselves, well, did we have any reason to believe that there were any search procedures that we should trust? And we used these as the criteria of whether or not we had such kind of search algorithms. The answer would have been really no. We didn't have a mathematical theory of why these algorithms should be correct or under what circumstances that they should be correct. We didn't have computer simulations demonstrating that they would be correct under these the assumptions of the simulation. We didn't have like improved performance on benchmark problems. We didn't have cross-validation or external validation of predictions. We didn't have algorithms that people were using in the field of application. We didn't have any success in the marketplace. So it looked perfectly reasonable in 1990 to say, well, there aren't any such algorithms. And we have reasons to believe that with this long list of problems, some of which we have no idea how to ever solve, like the unmeasured confounder problem, that we'll never have solutions to those problems. So when you have problems of this kind, such as non-identifiability, which we had recognized in the in the alarm network case, which we were sort of taking as a good kind of test case because we weren't worried about confounders, but we were worried about the number of variables and the non-identifiability, the fact that there were multiple causal DAGs which would entail the exact same probability distribution over the measured variables. What do you do when you have these kinds of problems? Well, there's a number of different things you could do. One thing you could do is strengthen assumptions. So one thing we did was to add this kind of causal faithfulness assumption. So it's a kind of simplicity assumption, but we added it so that, for instance, if I had a causal model which had more edges than the true causal model, that we could say we would prefer the simpler causal model, which had fewer edges, than the one with more one with more edges. So you can strengthen your assumptions, you can weaken your sense of success, because saying I prefer fewer edges doesn't get me out of the problem altogether, because there are some DAGs which have the exact same number of edges, but still entail the exact same probability distribution over the measured variables. So we decided, okay, if that's what was going to happen, instead of outputting a DAG, we would output a Markov equivalence class. We would output a set of DAGs, all of which had exactly the same d-separation relations. So, the two main things that we thought were, we will strengthen the assumptions to deal with non-identifiability, and we will, by adding causal faithfulness, and we will allow ourselves to output the Markov equivalence class instead of the DAG and call that success. That's not the success we wanted, but it's still a kind of success, and that it's worth doing that. there are sort of other responses that you can make to problems about non-identifiability. One would be to say, well, do the experiments. And certainly there were people that thought that's the only acceptable response. Do the experiments. We thought there were good reasons to believe we couldn't do the experiments and we wouldn't be able to do the experiments. So we rejected that. And then the fourth is to give up and say, well, we can't really do science in these instances. And we thought that was excessively negative. So let's strengthen the assumptions we hope in a reasonable way, weaken the sense of success, and proceed from there. So we came up with basically a constraint-based causal discovery algorithm. And the idea was we would use the conditional independence constraints between each variable pair in order to try and do a search which would allow us to find the correct Markov equivalence class. So the input for our algorithm would be the data for all the variables. We would do a bunch of statistical tests in order to determine which conditional independencies existed. And then we would do a search which looked for the set of DAGs in the Markov equivalence class, which as closely as possible entailed the conditional independency relationships that we had seen, that we had determined via statistical tests from our data. So that was the first thing we tried was the SGS algorithm. And basically, I'm not going to go into, I'm going to talk tomorrow about how the PC algorithm and extensions of it work and what its strengths and weaknesses are. So here I will simply say that we came up with first with the SGS algorithm, which did not entail that we needed to look at every possible causal model, which you may remember was, 10 to the 250th or something. But the first version did say we had to look at every possible conditional independence relation so we could test them. That still required way too many tests to be practical if you had a large number of variables, because you would have to look at, there would be n choose 2 pairs of variables, and for each of those n choose 2 pairs of variables, you would have 2 to the n minus 1, 2 to the n minus 2 sets of variables that you could condition on, and you would have to look at all of those. So that wasn't practical that was practical for small sets of variables like 10 or 20, but not for large sets of variables. So ultimately we came up with the PC algorithm, which didn't even require looking at all of the possible sets of conditional independence tests that you could do. It actually looked at a rather small, depending on how dense the graph was, it would look at a very small set of conditional independence relations. Let me skip over this. Okay. So you can prove that it gives asymptotically correct results about the Markov equivalent class if you don't have unmeasured confounders, and it wasn't in the proof, but it was implicitly assumed you also didn't have measurement error and selection bias and that long list of other problems as well. There are other constraint-based algorithms which give asymptotically correct results even if there are latent confounders, which we also developed. They rely heavily on the causal Markov condition and the faithfulness assumption. The faithfulness assumption is something we'll also talk about in the next lecture, which is something which is a very strong assumption. It turns out to be much stronger than you actually need, but even if you weaken it to sort of a sub version of the faithfulness assumption, it's still somewhat stronger than you would like. So there is that problem that makes the reliability on finite sample sizes much more dubious than the asymptotically correct result. That is, it says you will, if you have a large enough sample size, get correct results, but it might be that those sample sizes that you require are unrealistically large. It outputs an equivalence class, which is not what you really wanted. What you wanted was the DAG. So it might be informative enough for some of the questions you're asking, but not informative enough for the purposes of that you're asking about. So so a lot of what we'll talk about in this course is sort of dealing with the weaknesses of the kind of algorithm that the PC algorithm is, and how we can weaken the assumptions and improve the outputs. By making different kinds of assumptions, we can sometimes discover things within the Markov equivalence class rather than just that. I'm sorry, what happened? I don't know what happened. Give me a second. Yeah, my PowerPoint crashed, so I'm going to have to restart it. So yeah, so a lot of this is going to be about descendants of the kinds of algorithm that PC is, this kind of constraint-based algorithm, and but we'll see that there are also sort of other kinds of algorithms, such as algorithms which are based on scores, and algorithms which make distributional assumptions, rather than making the sort of simplicity assumption that PC makes. So I should say, so we took the alarm network to be this super hard problem. And the idea was we wanted to see if we could, even though it was simulated data and we didn't have to worry about confounding and we didn't have to worry about the selection bias, etc., whether just we could deal with the sheer number of variables and the non-identifiability problems that we had. so we were able, so we ran the alarm network through the PC algorithm, and it actually did pretty well, which we thought was groundbreaking. It rarely missed. It rarely added extra edges to the output. That was very rare, and it did pretty well on not omitting edges from the output. And in terms of the direction of the edges, which way they faced, it didn't do as well, but it still did well enough to be, informative and useful. So we had results about the asymptotic properties of it, and we had the simulation results. So in terms of the kinds of criteria that Gelman had suggested were necessary for somebody to believe that you should trust the output of the algorithm, we were starting to make progress on saying this is an algorithm which you should trust under this rather strong set of assumptions about, for instance, no confounding. But we took that long list of problems that made people mistrust algorithms, not as a sign that we should give up, but as a sign that we should get to work on trying to figure out how to deal with each of those kinds of problems. And that's kind of an ongoing activity in causal research today. I should say that the philosophy department at Carnegie Mellon is directly across the hall from the statistics department. And one of the most famous statisticians at the time was Steve Feinberg, who had literally written the book on the analysis of discrete data. And if you look at that book, then the examples that he uses in that book tend to be, something with 5 variables or 6 variables or 7 variables. And he did discuss search in that book, but the only searches he discussed were heuristic searches, where you wouldn't prove anything about them. And they were searches for undirected models rather than for directed models. So when we described to him what we were attempting to do with the alarm network, he kind of looked at that, and we told him that we had developed this algorithm which was pretty good at finding that structure. He just looked at what the true structure was, and he shook his head like, no, that can't be possible, right? And basically for the reasons about the size of the state space and the number of different models that we were looking at. So, when we showed him we were able to do it, he was pretty surprised, and we took that as sort of a great sign that we really had accomplished something. It turns out that lots of people have tested algorithms on the alarm network, and the alarm network happens to be particularly easy network to reconstruct from data because a lot of the edges are quite strong and it's not a very dense network. And the strength of the edges and the fact that it's not a very dense network actually makes it fairly easy. But we had no idea about that at the time. To us, it was just a super hard problem that we'd actually made progress on. Let me just say a few words about the other branch of causal learning, where we're trying to learn representation learning. What we're trying to learn is not so much about the measured variables, but we're trying to learn about the variables we haven't measured and how they're related to each other. So I gave you the answer, the example before about psychometric questionnaires, where we have the measured variables, but we're trying to, which are the answers to the questions, but we're trying to figure out how do your personality traits relate to each other. And let me say a little bit about the state of latent variable search, because people understood that the idea that looking for latent variables was a really hard problem, and that we needed it for structural learning, but we also needed it for this other kind of, where we were really just interested in the latent variables themselves. So a lot of the development of the methods for causal structure, for representation learning, are derived from Spearman's work. So Spearman showed that a necessary condition for there to be a single factor to linearly cause 4 measured variables is that the following 3 tetrad differences vanishes. Where the R's are the correlations. So the correlation between 1 and 2 times the correlation between 3 and 4 minus the correlation between 1 and 3 times the correlation between 2 and 4, he showed that that would be 0 regardless of what the linear coefficients were if you had that causal structure. He was interested in this because he was trying to show that there was a single factor, general intelligence, which could explain all of these different test results. So, that's it wasn't so much a search method as it was a kind of test method, where you would try and show that, try and find, can there be a single factor explanation of the correlation matrix among a set of measured factors. Now, of course, you can also explain the zero correlation, the zero tetrad constraint with an alternative model in which every variable, there aren't any latent variables, but every variable is a cause, every pair of variables has an edge connecting them. However, that alternative model, while it's compatible with the vanishing tetrad constraint, does not entail the vanishing tetrad constraint. So in that case, it's actually a more complicated model. And so again, you would invoke a simplicity principle to choose the simpler model. Factor analysis was developed in 1935 by Thurstone. And again, the goal was to identify a small number of factors that explain the correlation matrix among the observed. And as I mentioned earlier, the factor analysis, there was quite a debate about whether this was a model that was to be interpreted causally, or whether it was simply a parsimonious representation of the correlation matrix among the measured variables. And if you look at factor analysis textbooks, say as late as 1960, Harman was the standard textbook. He says the primary goal is to attain scientific parsimony or economy of description. But it is, of course, possible to give factor analysis a causal interpretation. But then you need to worry about the condition. You would need to prove things about when the factor analytic coefficients that you come up with are going to be the same as the causal coefficients. So that's an active area of research now as well. And then in the 60s, it was Herbert Kostner, who was a social scientist, looked at a variety of different cases where these vanishing tetrad constraints held, and gave some conditions under which you would see some vanishing tetrad constraints, even if it wasn't a single factor model. And then in 1987, we developed the tetrad representation theorem, which was a general relationship between tetrad constraints and linear graphical models. So we gave sort of exact conditions under which you could look at a given graphical model and determine whether or not a vanishing tetrad constraint was entailed. And again, that has set off a whole set of a branch of research into extending that kind of search, but weakening the assumptions and looking at a wider variety of different graphical models. So let me just state that at this point in time, I think if you go through Gelman's list of reasons to believe that we can trust the output of a search procedure, that starting in the late 80s and early 90s, we began to have sort of reasons to trust the the output of some search algorithms because we were able to sort of reduce the strength of the assumptions that would be necessary, and we're able to give actual proofs of conditions under which the output would be correct. And so those are the ones with the green check marks. But that's very much sort of an ongoing research project, which is sort of the topic of what we're covering in this course. So let me stop there since I've run out of time. And that the stuff at the end was sort of stuff that I wasn't sure that I was going to get to, and isn't exactly the history. It's more about the contemporary state of things. So as far as the history is concerned, let me stop here.
Thank you very much, Dr. Spertis, for a very interesting lecture on the histories. I guess we can take a minute or two if anyone has questions. Yeah.
Very nice talk, Dr. Spertis. This is Kai Wang. I'm from University of Iowa. So my question is this: you talked about the SEM. As far as I know, econometricians, they are interested in this equilibrium status.
Yes.
So my question is, if the data from this equilibrium status, I mean, how can you derive this causality relationship? It's like a chicken and egg, which one comes first?
Well, I think the representation, if you put cycles into the, let's put it this way, the graphs that would come out of extensions of sort of things like PC and FCI, which assume that it's a directed acyclic graph, are they allow for cyclic relationships, and those so some of the relationships that would come out would be acyclic, and some of them the relationships would be cyclic. For the cyclic ones, there actually is, depending upon the assumptions that you want to make about the distribution, you would be unable to determine the direction of the cycle. That is, whether A caused B, caused C, caused D, caused A, or whether it went the other way around, that A caused D, caused C, caused B, caused A. So in that sense, you wouldn't get an answer about which way the cycle was going. If you're willing to assume something like linearity and also non-Gaussianity, there may be cases where there's less underdetermination. But generally speaking, under certain conditions, it's just not identifiable which direction you're getting, and the output will tell you that it can't identify which direction things are going. And that's the best you can do.
Any other questions? Oh,
Well, I have a follow-up question. I have seen people doing these things, so they want to infer the causality direction, right? So they do 2 regressions, then do the test, and one is significant, one is not. Then you see, I mean, the significant one represents the true direction of causality. Is that okay?
Well, no, because generally speaking, whether or not the regression coefficient represents the strength of a causal relationship depends not just upon, it depends on the entire set of variables that you're regressing on. If you have the wrong, so simply flipping the direction of one edge might mean that in both cases, you're not getting the regression coefficient won't be a good estimate of the causal coefficient. So in that sense, in both directions, you'd be getting a coefficient which just is not representative of the causal coefficient. So flipping a single edge is not correct. You need to regress on the right stuff, on the right set of variables. And flipping an edge doesn't guarantee that you're going to get the right set of variables.
I have a question. Well, more about history. You mentioned that Fisher, I guess, he spent a lot of time trying to come up with alternative hypotheses that maybe there are some latent confounders that confounds smoking and lung cancers. Well, Fisher being Fisher, who, believing firmly randomized control trial, did he or someone else or some epidemiologist at the time consider just do experiments, not on human, of course, but with animal models? That should, in principle, settles this alternative hypothesis. There's a common confounder.
Yeah, there were a number of things that people did. So one is to look at identical twins. There were animal experiments whereby people placed, they would paint sort of tar and nicotine on the lungs of animals and then see if they developed cancer. It typically, however, there's problems, of course, with animal experiments and how well they represent what's going on in human beings. And typically, they would give dosages of smoke and tar and nicotine to the lungs that were sort of outlandish by human, in the human case. So yes, those did exist, but they had randomized trials don't solve all problems, right? Those were not the dosages that people were getting. They were much, much, much larger than what people were getting. And of course, the animals are just different species than us. And there's lots of things that occur in animals that don't occur in people. So there were those worries. So people certainly took those things as sure, that's evidence, but it's not conclusive evidence. And so there was this kind of demand that, well, science ought to be able to do more than say, here's kind of heuristic reasons to believe that there's sort of good evidence, that we need something stronger than that, or at least better science would require that. So yeah, people did look at that, but they saw flaws in all the things that had been done as evidence, but just not conclusive.
Okay, thanks. I have another sort of, again, question related to history. You said that, when Pro sort of invented or came up with Bayesian network or DAGs in the 80s, it's almost like a strict special case of SEM, which was invented, let's say, in early 20th century, just without cycles, without latent confounders.
Without confounders, but he extended it to sort of, everything that Wright had done was all linear. So this was, in a sense, a huge generalization in that all the stuff about conditional independence was not anything that anybody had derived certainly for any nonlinear case in structural equation models. And it was also applicable to the discrete case, and it came along with the ability to calculate conditional probabilities in a reasonably fast manner. So for all of those reasons, it was just applicable to a whole slew of cases that the structural equation modelers never would have thought of.
All right, thanks. Any other questions?
Okay, thank you.
Thank you. I have got one question that is actually about the switching the causality directions. So it's just a simple hypothesis saying that, okay, we have X and Y's and we are doing a simple regression at this moment. So obviously regression from X to Y and as a direction is quite different from Y to X. But is that possible to just using Bayesian rules to actually do that?
Sorry, to use what?
Some other using the Bayesian theorem to do that just by the switching the conditions?
I don't.
So the probability of X given Y transform into probability of Y given X using the Bayesian rule. Is that possible to do that? To switch the direction?
So for instance, in the Gaussian case or the multinomial case, you would get a symmetry that there is no, how shall I put this? You can calculate those in each direction, but it's not going to tell you the direct. In the Gaussian or the multinomial case, there's nothing about the distributions that would distinguish which direction things go in. What we'll see later is that in the case of, say, linear non-Gaussian, or in the case of additive noise models, it will be possible to check the direction that an edge goes, because there will be an asymmetry about whether the residuals of the regression are independent of the regressors. So the answer to that is yes, under certain assumptions. So you have to fall within certain classes of distributions and not other classes. And you have to make some assumptions about what class of distributions you're dealing with in order to be able to draw that conclusion. But we'll see later that yes, pairwise is possible under certain distributional assumptions, basically using regressions.
Thanks. Any other questions? Okay, if not, then let's thank our speaker, and we look forward to your lecture tomorrow. Thank you very much, Dr. Spritz.
Thank you. Goodbye.